Hello. So a couple of warnings about this talk. Firstly, bad puns. Databases are like fish. There's plenty of databases in the sea. Tenuous image choices, etc. Secondly, I'm going to be going through these slides quite quickly. I'm the sort of person that likes to have slides as a crutch for when I inevitably forget my words. So there might be a lot of content. Don't worry if you miss any of it. The slides are already online. Let's kick off by I'll very briefly introduce myself. I'm a technical lead at Softwire. Softwire are one of the sponsors here. We do lots of things. Come and talk to me if you want to know about any of them. But I'm more than just corporate pitches. I have a fun side as well. My interest is databases. I really enjoy working with lots of databases. My background was in statistics, simulation, so academic data analysis. And I like to hack around with data and see how data is used on different projects. Swam with Turtles on Twitter. Please feel free to mention me, follow me. I've been on TV. That was really exciting. But I'm a political nerd as well, so let's get down to some serious business. I really care quite strongly about politics, strongly enough to talk to you about what I think is one of the greatest political campaigns of all time. And it was the AV referendum. So in the UK, a little while ago, we had a big vote. If you guys aren't British nationals, you may not have seen this, you may have passed you by. We had a big vote as to whether or not we should rejig our voting system. Currently, we use the first past the post system, and essentially that means that the person who gets the most votes is the person who wins the seat and then goes on to represent that area in politics. And people thought that this may not be fair because if somebody gets 49% across the whole country, well then maybe that person actually deserves more representation than they get. And people decided to so when the Lib Dems got into power, they decided to work out whether or not we should change this system. And the Yes campaign were like, yes, it's much fairer. Everybody might have a chance to, vote less tactically or things like this. And they came out with some very good arguments as to why we should move to the AV system. The No to AV system ran a campaign such as this one. Under AV, the loser can win. Essentially, they argued that when we move to the AV campaign, the winner might not be the same. It's possible that with the same votes, we might have a different winner. And I sat there and thought, that's exactly the point. That is exactly why people are running this campaign. Because if we had the same winner all the time, then obviously people are going, what's the point in changing this system up? The Yes campaign managed to entirely reframe the vote. They were essentially saying, the No to AV campaign was essentially saying, well, surely the person who gets the most votes should be the winner. And under this new system, they won't be. They managed to turn around and claim that the Yes campaign's message was that a new system could get us to the same place better than the old system. That wasn't what the Yes campaign was saying at all. The Yes campaign was saying, well, maybe the old system isn't the right thing. But the No campaign got to come along and actually dictate the message and the question of the debate and really kind of shook the public psyche to believe that this is what we were debating about. I'm not trying to say whether or not the AV system was better or worse, despite the fact that at the last general election we had the least proportionate vote ever. Not trying to say whether it's better or worse at all. But what does this have to do with databases? I've been ranting for about 4 minutes now about politics. When we look at the current technical ecosystem, there is one very clear current leader. When you sit down to write a web application, especially this is very, very true 5 years ago, it's still true today, you will almost always just be using SQL by default. You won't think about what else to use. You won't think about all of the different kinds of databases to use. By default, you'll just plug SQL into your application. Especially on, say, the C# ecosystem and the .NET ecosystem, it's just taken a standard that you're going to use SQL Server. And all of the default plugins and libraries that you're using will factor into that. All of the discussions of database schemas that you see will, again, factor into SQL. There are better developers than I am who are talking about NoSQL databases. If SQL is so good and so mature and has such good support for all of the things we want databases to do, why are they doing this? It's exactly the same question that the No campaigners, the No to AV campaigners were trying to get you to think about. It's not that we think that NoSQL databases will do the things SQL does, but better. It's that we're saying maybe we're judging SQL as a database against the wrong standards. Maybe if you think that SQL is the right database, it very, very well might be for replication, but maybe you're not asking the questions that get to the heart of why are we choosing a particular database. So every time you hear yourself saying, well, this particular NoSQL database, this flavor of NoSQL database, can't do a thing that something else can, maybe it's not meant to solve that problem. Maybe it's actually the wrong database for this instance, but it would be very relevant on another database. So today, I want to be asking two key questions. The first one is, what are the sorts of questions you should be asking when you're choosing a database? And then, depending on the answers of those questions, what are the flavors of SQL or NoSQL database that are out there in the wild that we can be using based on those answers? So the first question I really want to talk about is the size of your data. And specifically, what happens as your data gets bigger and bigger. Because SQL is a mature database. SQL has got very good things built into it that allow it to still respond well, to still store data well and respond to queries quickly as you grow the database larger and larger. But eventually, it will grow so large you need to spread it across multiple different systems. And that isn't a problem with SQL. SQL, especially recently, has been getting more and more functionality built into it to allow you to scale your databases out. That's not an issue at all. Especially with, so Oracle are opening up their plugins as well. So when Oracle starts doing something, you know that almost all of the other SQL databases probably have this functionality in it as well. What happens when one instance of this distributed database goes down, though? There's a big theoretical discussion around when you distribute data, what happens when one of the places that you distribute data to goes down, or when, specifically, when the other databases in your partition, in your database cluster, can't talk to it anymore, when there's a network failure preventing it being talked to. And there is a very famous theorem called the CAP theorem. Are people familiar with the CAP theorem? There's some nods and some shakes, so I'll just very quickly run through it. I say quickly, there is a lot of thought in this area suggesting that maybe we're thinking about this wrong as a development community because the CAP theorem is a very abstract principle. Maybe we're not applying it right in the real world. There's a very good article here. Again, you can go and look at that. The slides will be online, which is called Please Stop Calling Databases CP or AP. So there are two kinds of databases. There are CP and AP databases. In CAP, there are the three letters CAP stand for consistent, available, and partition tolerant. Partition tolerant essentially says if the database still kind of sort of works if the networks cannot, if there's two nodes in your cluster that you can't communicate across. Assuming that you've got a partition database, you're always going to want partition tolerance. So that's not up for question. But the question is whether or not you want consistency or whether or not you want availability, because you can't have both. So if we've got this distributed data, it's obviously storing the best animal data, the most important data, which is why it needs to be so robust. Currently, the data in there is wrong. So we update it. The write to the database goes into node A. And then if all of the data bases are working, it will replicate across to C and B, and we've got all of the data in the correct place. So that is how data propagation will happen in a clustered system. If the links to database C go down, and then we want to update one of the nodes this time, let's first of all start thinking about an available system. So what we mean by available is that regardless of the state of the network, we can get an answer from every single node. Every single node in the database is still giving us answers. So we still want, even though the database C is not connected to the network, it should still be giving us things. So when we talk about availability, if we update node A, it will still propagate to node B, but it won't propagate to node C. So this is what we mean by inconsistent. The database is inconsistent. Depending on the database, depending on the machine that our request goes to, we might be getting different data back. It's not in a consistent state. If we want consistency, in this case, we have to trade availability for it, because there's absolutely no way that if we write to the node A, that it can get propagated to node C. So if we want to have this highly consistent system, then we just have to get rid of node C from our database and assume that we can read from the other two. So we get to choose when we partition our data, whether we want a consistent or an available database. And it's a good question. There's genuinely, I don't think there's a right answer to that question. Depending on your domain, you have to think very carefully about which of these two things that you want. So if you work in the stock markets, you'll almost certainly want consistency, because you can't be dealing with data that's milliseconds out of date. You can't be dealing with the wrong data. If you do, you may make transactions that cost you millions of pounds. So there are definitely systems for which consistency is more important. But I think in your applications, and a lot of people do this, they overvalue consistency. They kind of say, well, we absolutely need to know this data 100%, and we'll take some of our systems going down in order to accommodate that. Amazon realized this problem, and they wrote a big white paper about an implementation of databases called Dynamo. So Dynamo is a standard that databases might adopt, and specifically what it's talking about is sacrificing consistency in order to give you a more reliable experience. Because it doesn't matter if Amazon report that there are 14 of an item left when there are actually 12, and the database will catch up to that very, very quickly. And we're happy to take this slight sacrifice of consistency as long as it does catch up eventually, because the cost of you slightly misreporting something is significantly less than the cost of one of your systems going down to accommodate this. And so Dynamo was a standard that they wrote that makes sure that that is applied in your databases. So just like SQL, there's lots of different flavors of SQL databases. Many different people have written their own implementations of Dynamo. So Cassandra is one that is very, very famously deals with large amounts of data. You can use that as a column store database, so you can sum and aggregate things over the entire column, and there are other use cases for it as well. React is one which is a lot more lightweight. So React is just a very, very lightweight implementation of this that will very quickly be set up and allows you to get the consistency, allows you to sacrifice consistency, but be highly available. As we said, the cost of this is that you don't get guaranteed consistency in your database. Amazon are okay with that, but other companies might not be. So let's think about Facebook. Specifically, let's think about Facebook's messaging system. There are lots of messages on Facebook. There are too many messages on Facebook. People talk rubbish on Facebook. And they just fire messages backwards and forwards, and there's billions, if not more, messages in the Facebook system. But it's got a very interesting shape to it. When people access the message data on the social media site, you'll find that they more often than not just look at messages that have been sent in the last seconds to minutes. They don't care about these old messages. Nobody goes back and reads 2-year-old messages that you sent to random people, or at the very least, it's very, very few people do. So there's a very, very large amount of data, and there's, most of them are being read at the beginning. So Facebook decided to start looking at what can we use to store these messages in the database, and the first thing they thought of was MySQL. They want it to be available. They wanted to always be able to see it. And MySQL is something that is good. MySQL is a good messaging system. But the problem with MySQL is the size that the indexes will take up in memory. There's so much data in this system, and it goes on so long that any index is going to be massive, and any index will not be able to be stored on one machine. It's just, the indexes started taking up much more space, or not more space, but enough space that it wasn't being able to be stored. So they couldn't use MySQL as a solution to have fast data. And then they considered Cassandra. So Cassandra is one of these Dynamo implementations we talked about. So it's eventually consistent. It's not consistent at this moment in time. And they found that the number of machines that they would need to scale Cassandra out this widely, it was just too many for the data to be propagated in any sensible time frame. They found that because of this really kind of massive, massive peak in the short term, it wasn't sustainable, it wasn't suitable to use an eventually consistent system because the data just doesn't propagate through it quickly enough. So they wanted something that would be able to give them this immediacy of data in the short term, but also being able to deal with this large tail of data. They used Hadoop. So Hadoop is an ecosystem of a large number of different tools. specifically focused around being able to distribute your database across a large number of clusters. So it enables the distributed processing of large items in memory. There's loads of different things that you can build over Hadoop. Hadoop is a wide topic that I am not going to take a step into today because you can talk about it for hours at a time. And if you're ever at a conference that has a Hadoop session, it's a great thing to know about and have in your arsenal. But essentially, the way that it works is by having small numbers of nodes, or the way that they were using it was using a framework called HBase. It has a small numbers of nodes which are in charge of making sure that all of your databases are able to respond very quickly to your requests. It will basically have name nodes which delegate out requests to individual servers because it knows where the databases are. It's essentially a way of sharding your index across multiple machines. And if any of those nodes go down, all of a sudden your data may not be accessible. So that again, they sacrificed availability to do this just because the eventually consistent machines weren't able to cope with the speed at which they needed data directly in their browser. We've talked about large amounts of data. We've talked about times when we have to make sacrifices in order to store the sheer volume of data that we want to. But there will be times that we actually don't need to distribute, that we're very happy to store data on one machine. And if we are happy to store data on one machine, instead of having to make sacrifices, like for consistency or for availability, maybe we get bonuses with our data. And one of the ways that we can do that is by actually using our database to kind of have our data model reflect the shape of the data in the domain that we're modeling. Let's talk very quickly about SQL. SQL, big, famous, standard acronym, in which every row is a thing, in which we store everything as an item in the database, and every row represents one entity, which is almost always one thing in the real world. Data is read out and interacted with in a set-based way, so there are a limited number of ways that you can access your database in the way that SQL wants you to. You can use where commands, which will essentially be able to intersect your data and only return some of it. There are unions, so here we're combining all of our favourite fictional mammals with all of our favourite fictional fish. And there are joins. You might notice a slight anti-cat propaganda in this presentation because cats are just used far too frequently in techie presentations. Joins, where we're taking this row and joining it with some denormalized coolness ratings, are just Cartesian products of the tables, and then we're doing an intersection on them. So SQL has a very limited number of ways in which you can read data out, and if you do that, great. SQL loves you. It will give you all of the 40-plus years of power that has gone into the development of SQL. It does it well. You can model objects which have got a fixed structure because of your schema. You've got fixed rows which tell you everything that your items need to be. If there are relations, you can join them. If you know a number of relations, it's much easier to join them. If you start having to go into recursion because there are weird depths of relations or amorphous numbers of hierarchies, then that's harder. But SQL is just a good all-round tool that you can use on any project and spin up tomorrow to model your data. But there are problems that this is bad for. There are problems that SQL does not work massively well with. Are you familiar with the 6 Degrees of Kevin Bacon? It's Kevin Bacon, very prolific actor. So prolific, so famous for taking part in bad and gratuitous movies. Gratuitous in that they shouldn't have been made rather than for the content. That he got this reputation for starring in movies with lots of people, with lots of actors. And actors started taking it as a badge of pride to work with Kevin Bacon or be close enough to Kevin Bacon on the list of people that they have worked with, that Kevin Bacon has worked with. So they came up with this idea of a Bacon number. Your Bacon number is defined as the shortest path on the film acting co-starring network that you can find between yourself and Kevin Bacon. That is not good to be modeled in SQL. SQL is not particularly good at finding these lengths of paths. And there are ways to do it, especially in SQL Server. Common table expressions allow you to recursively join this co-starring relation along the graph, along the network. But it doesn't do it natively, and it doesn't allow you to utilize the power that SQL has. There's no efficient way to do that in the original SQL standard. Going back to my political nerdery, in 2014 there was a very good hackathon called the Hack the Government, and we discovered it was, this was the year before the general election, we discovered that there was no open election data, and we wanted to find a way to open out, to make an API where we can where we can just distribute the information so that people can find the information, hopefully through a RESTful or so API. We found the data. We found all of the data on one particular professor's website. We weren't able to open the data up because we didn't hear back from him, and we didn't have permission to share that data in that case. But we were able to scrape the data off his website, put it into a database. Oh, so it's fine to scrape data as long as you don't give it away, I think. Throw it into a database and then release it. There's a couple of interesting election trivia we found out, just purely by certain things not being in the same shape. A couple of elections were once held using STV. So the Cambridge University, I think it was, used to have a constituency, and they just held their votes for STV just for the fun of it early on, rather than any kind of sensible first-past-the-post systems. But when we were looking at the election data, we were thinking about what people want from election data. And people don't care about David Cameron. People don't care about David Cameron because they care about why David Cameron is in the position that he is. You'll always, if you go and ask questions about David Cameron, you care about the constituency that he is in, or you care about the party that he represents, or about the position in that party, or about the elections that he has won. So when you ask questions about him, he as an entity is almost meaningless. But what you care about is how he links up with other items in the graph of different types. And this, again, is something that SQL can do, but in order to find out his constituency and his election results and his party and everything like that, you would start having to do lots and lots and lots of joins. And joins, although a way of solving a problem in SQL, are not necessarily something that SQL is designed to do in a particularly excellent manner. And that's when we started looking at Neo4j, or specifically graph databases. So graph databases store these items. So these entities are being stored as nodes, again, so if index is over them the same way that you would store rows in SQL, but all in one big mess. The key difference between Neo4j/graph databases and other databases are these relations as well. These relationships between these nodes are stored as first-class citizens. And that means that they can be read in as constant a time as your nodes can be read out in. You don't need to be doing expensive O-log n joins, or whatever SQL has managed to do now, in order to join your data together, because the relations are right there next to your nodes in the database. So you can start doing these queries very quickly. So I mentioned Neo4j, that is the name of a kind of graph database. There are other graph databases available, including Arango, which calls itself a mixed model database, but really everyone who uses it for the graph-like nature of it. What we mean by that is that it stores nodes and edges in the system. It is embedded, it is disk-based, it is fully transactional, it's Java, so you can run it in your JVM or integrate to it with a REST API, and it stores data structured in graphs. So rather than all of your things just sitting lonesome in your database, it's storing the edges in there as well. All of the nodes and edges are stored as first-class objects in the database. They're all typed. So you can give a node a type, such as this is a politician, this is an election, this is a year, and then all of the edges have types as well. So this type could be stood in. So David Cameron stood in 2010, or stood for. So David Cameron stood for the Conservative Party, and so on. And all of these nodes and edges also double as key value stores. So you can have on the stood in edge, representing David Cameron's kind of standing in a political election, you can have the number of votes that he got in that election, say, on the edge. So as I mentioned, joins are first-class database objects. You don't need to do the expensive join operations, and certain queries become trivial. The 7 degrees of Kevin Bacon is really easy in this because there is a shortest path to function in Neo4j, which I am almost certain was made just so that people can talk about how good it is at storing Kevin Bacon, not the person, the node. You get what I mean? So it's very, very good to do that sort of query that in SQL is very expensive. And in SQL, you have to start thinking a lot about how do I write this query. It will be lines and lines, and it's one line in Neo4j. It's very easy to use, very easy to work with. It is probably my favorite database, but I don't want to be as much of a data geek to admit that I've got a favorite database. It's mature, though, and that's the key thing. All of these people, it's quite hard to see from this distance, all of these people are using Neo4j. This is an image taken directly from their website. On the top, it represents the sorts of websites that they're making, and on the left, sorry, other way around, on the left, it's representing the kinds of software that they're making, and on the top, it's representing the domain that they're in. So you can see media companies are using it, energy companies are using it, and they're using it across a whole range of types of software, including social networking, including content management systems. So if you go to your board tomorrow and say, I want to use Neo4j, you've got large amounts of evidence behind you. And the reason that I bring this up is because a lot of people think of NoSQL as this really immature movement. But actually, it's been growing really strongly, and a lot of money and a lot of energy and effort has been put into the development of some of these frameworks. Not just Neo4j, it's just they had the image that was easiest to steal from the website. Sometimes SQL, sometimes these high-fidelity data model databases are really overwrought. Sometimes you think, do I really need to be able to store all of that data? Do I really need to have this complex structure? Sometimes you don't. Sometimes you want something really simple. And spinning up this whole massive SQL instance is just a drag. Sometimes you want to just, I just want something that will persist across my scaled application to prevent all of them running the same scheduled jobs. I just want a really basic lock mechanism. Sometimes you want a really basic cache. Sometimes you just have, well, I know the kind of hashed user ID of this user. I know that they've cached some data in this database. I just very quickly want to be able to retrieve it. You don't need SQL for that. You can use it, like indexing, fine. You can use Neo4j if you really want to. But sometimes they're just too much. Sometimes using a key value store is the solution that you want. So we kind of talked about this high-fidelity data model in which all of your data is stored in the kind of way that you can see it in the real world, and because of that, it will give you a more powerful range of queries to run. Key value stores, all the way down to the opposite. They are literally just an ID and something you can pull out of a database against that ID. And they don't really, values are typically, in these sorts of databases, JSON objects. So you can have some level of, complicated stuff there, but it doesn't match any of the complicated data structures behind it. These weren't just random examples I pulled for this use. Both of those two examples are used by BBC and Twitter, respectively. So for caching, Twitter uses Redis, which it uses in a key value store way to pull out the cache of what it's got on your timeline, so it doesn't need to reload everything each time. DynamoDB, which is the AWS key value store, is used by the BBC, again, both for caching and they use it to lock so that scheduled processes don't run at the same time on all 4 of your instances. As a subset of key value stores, one of the benefits that we can get by choosing a very simple data model, not just the ease of setup and the ease of development time, you can get some more power by choosing a very simple database. So there's such thing as a time series database. So TempoIQ use time series database as a service, which means you upload all of your potentially Internet of Things data to it with a timestamp and a value. And all you get from this timestamp and value is a database that looks something like this. And it might sound really silly. It's a bit like, well, I can use SQL for this. It's in a table, I can use SQL. But because they've chosen a very specific domain, because they've chosen a very specific kind of data, they can give you a lot of value for free. So if you wanted to do interesting time-based aggregations, then SQL can do that. But if you want to aggregate it into something like a day, you'll need to educate SQL about what a day is and how to aggregate it like that. It comes for free from TempoIQ. If you have a missing row, if you've got things regularly at 15-minute intervals, but for some reason your temperature Arduino didn't send a message back for one of those 15-minute periods, Fourier analysis is built into TempoIQ, so it can actually interpolate what the value missing is. So this is the sort of thing where using SQL would be absolutely fine, but by being a little bit more specific about what you want and by being happy to make trade-offs in other areas, you can get some more stuff out the box on a more specific service. And there are problems that SQL is just too strict for. SQL, we saw big table, lots of rows, lots of columns. You have to fill in all the columns. You can have nullable columns, but having a billion different nullable columns, of which 3 are filled in for every row, is just silly. And the New York Times discovered that when they were making their freelance submission page. So the New York Times has a large amount of freelancers working for it, and if you have a video or a photo that you would like to upload, then you can do that to the New York Times' website. I know that we've got a published journalist in the house who recently uploaded his photo of the fire in Bristol, and did so on a similar site. And I'm not going to name any names because he's already blushing like mad, but he's just there if you want to look at him. You want to be able to upload your site, your content to the New York Times. There's different metadata about all of the different objects that you might upload to the website. So a video has got a duration, whereas a photo has got a location or a resolution or something like that. And to have all of these in the same database schema would be wrong because they need different metadata. And so the New York Times did use a database that actually gave you the schemaless effect, that you could put whatever you wanted to into the database. They use MongoDB for that, which was a big famous poster child of NoSQL. It's the first one that people popularized. Essentially, it just stores JSON blobs that have very little relation with each other. Diaspora also used MongoDB. Diaspora, a big famous social media site, decided that MySQL was wrong for their purposes, or any kind of SQL flavor was wrong for their purposes. They discovered the hard way that MySQL was very much right for their purposes. They had a very expensive rewrite of their system because they didn't think about the questions that I'm telling you today, or at least I assume they didn't, otherwise they wouldn't have ended up with Mongo. The problem is that in a social media site, you are a user, and as a user, you interact with other things. So when I like your post on Facebook, there needs to be a reference from me having liked it back to my user, so that if I change my name or change my profile picture, that updates on that part of the document later. So SQL does that very well by denormalizing, so that you use foreign keys to point to that data, and if it changes, that's fine. Neo4j, we saw, does that very well by actually just having an edge that points directly to that data. MongoDB does not do this. If you want to have this coolness rating that is related to the species, then you either have to put it on there or start re-implementing foreign keys by having IDs to a different coolness rating somewhere else, and that proved to be very expensive. And because of that, they had to rewrite it going back to SQL. So there are problems that SQL is good for. This is not a SQL is evil talk, very much so. It's very much not a SQL is evil talk. It's maybe everything's good and lovely. Not everything's good or lovely, because some things are really expensive, really, really expensive. And like, if you work for a bank, they'll probably be willing to pay that much money for Oracle. If you work for a startup, they probably wouldn't be. So it's a really trivial point to mention, but when you are about to choose a database, do double check the licensing. As NoSQL becomes bigger, a lot of companies have interesting licensing conditions, will require you to pay to use it on a site that you don't release your code for example. These are the two examples of the people that are just taking the mick with their pricing structures. There are other ones that are free / basically free / some of them are open sourced. So I don't have the time to go into all of these, but yeah, just think when you're setting up your project, before you architect this lovely architecture around this new database, double check the pricing of it, just because it does vary significantly between databases. The last thing I want to talk about is the use of data and what consumes the data that's in your database. So I know it's really hard in the software industry, and I know it's really, really kind of a pain, but we do have to remember that people use our software. We're not just writing it to keep us in a job. we're not just writing it because we love spending all of our time kind of writing the perfect Java method. Some people would argue that doesn't exist, but because it's Java. So when you think about your application architecture, very, very simple layered architecture here, we've got the database, we've got a code that wraps it, and the data is being thrown out. We have to remember that the data is actually going to somewhere, it is going to the end user, and that every single one of these places on this kind of very crude architectural diagram has to shape where we've got the data. Because, I mean, I know we talk about wanting to decouple our code. I know that we would like to write a front end that really doesn't care about the database structure. But if your end user is asking the question, what is the average age of all of the people in this room, then you'll definitely want to architect your information and your data differently than if they were like, oh, something like Campbell, because Google has very, very different needs than Google the search engine and PageRank and all of that sort of thing has very different needs than Google Sheets or whatever nice relational data you're using. I'm not arguing that we tie our front end directly to our database. I'm very much in favor of having a nice decoupled layered architecture. But we do need to think about the kinds of questions that will be coming back so that we don't end up having to write a big, expensive interpretation layer between the front end and the back end. In fact, sometimes writing this decoupled architecture is good for this sort of thing because you find that the questions that users have of your data or your understanding of what the users need from your data changes over the course of a project. And therefore, you might start using SQL and then discover that the big thing that a user wants is this kind of fuzzy matching on Campbell. And then you might have to start thinking, well, actually, I might need to change the back end based on this new information. So our choice is informed by our plans for the application. Thinking about Foursquare. Foursquare is it's from a generation of social media sites where social media decided to just try and make everything shareable. So Foursquare was like, share your location, share the restaurants that you go to, etc. And what they really cared about is being able to see people that were near you, because that's not creepy at all. And so they decided to use a database that had geospatial indexing. What we mean by geospatial indexing is I want to know all the people that are close to me. I want to, there are ways to do this using SQL. You have an X coordinate and a Y coordinate, say, but there's no good index in SQL or in earlier versions of SQL Server that will allow you to say, well, I actually want to index it based on the kind of square root of the hypotenuse, or the square of the hypotenuse between here and there. That sort of indexing, where it's an index with a parameter of where you are as a function of two columns, that just doesn't exist. So people have built databases that can do that. When Foursquare were around, MongoDB did that. They chose to use MongoDB. Since then, a lot of other databases have added geospatial indexing because it is quite a good use case, especially when people are wandering around on their phones. But at the time, because it was so important for them to have location data, they couldn't choose any of the databases which didn't have this geospatial indexing. The Redbull Media house, I worked in PR for a little bit, so I'm going to go on a quick rant about PR very quickly. When you read a newspaper and you read an article, if that article mentions something about a company or a person, it is very likely that that company or that person wrote that article, uploaded it onto a website called a PR hub, and got all the really cheap journalist interns to go onto this website and be like, oh, we've got 13 pages to fill in the newspaper today, let's just download that. All of the property adverts you read in your newspapers are almost certainly written by estate agents. All of the fashion, almost certainly written by high street stores. And because of that, these sites like the Redbull Media House exist. They are just a place for people to go and upload content onto their website. But cheap journalistic interns kind of can't be doing this entirely because they do need to have something different to the paper next to it. And so the Redbull Media House did this really clever thing, which made it very easy to discover two similar articles, or articles about two similar themes, so that these interns could go pick up one article, see, it's got the same thing. It's got, a link to this other article. Maybe this article is about a skater and this article is about the skater's wife, say. But to do that, they needed to link in with other data sources which had information about the things that were in the article, so there could be that underlying data structure above it linking the articles together. And that standard does exist. It's called the Linked Media Framework. It is currently in development. It is a standard that allows you to link your article data to a higher data structure, to other data stores, and there is a database that will give that for you out of the box. It will allow you to integrate very easily into this higher level kind of ontology of information, and allows you to kind of use that for free and integrate these things together very nicely. Apache Marmot has only been used by this one company as far as I can tell. It's very new. So this is, out of all of the things in your talk, this is a thing to have the most skepticism about if you go and use it on a project tomorrow. The last thing I want to very briefly talk about is these two companies. Normally, if you have these two companies on a slide in the talk, this is the one that's like, what database do both of these two companies use? It must be the right database. It must be the thing that we use for everything. And specifically, we're talking about how it uses Elasticsearch. Elasticsearch, I gave the example earlier of fuzzy matching on something like Campbell, where you've got the word Campbell and you want to see something that looks like that. Maybe I've typed it in wrong, and you want something a bit similar to it. That would be very hard to do from scratch. There's a lot of really interesting ways that people can misspell things. Sometimes they've heard the word and they write it down phonetically and you want to search for it in that way. Search is a really hard problem with lots of moving parts. And so because of that, we don't want to have to work out those moving parts from scratch every time. And that's where Elasticsearch comes in. You throw all of the things you want to search across into JSON documents, and you throw the JSON documents into Elasticsearch. And then it's got Apache Lucene on top of it. Apache Lucene is a Java framework that essentially gives you lots of very powerful search functions on top of the other ways to query your database. So it's focused around text search inquiries, so that when you're asking for things from your database, you can still do the same kind of, I want all of the people whose hobbies are skateboard, but you can also do a fuzzy match, which allows you to say this person has misspelled skateboarding by missing out the N, and it allows them to search, and that will work because of this fuzzy operator. You can also give it parameters to say how much fuzz you're willing to kind of tolerate. And then you can also do more complicated queries, building it up like this, so telling it that you want a phrase and building a phrase into it and parameterizing things like that. Again, so the point that I'm saying there is that if you were trying to do all of these different ways of searching between things in a traditional SQL solution or in a large number of other NoSQL solutions, then it would be really hard. You would have a lot of work to do. You'd have to do a lot of it from scratch. And so this is a way that allows you to just get it out of the box if you initially use your data, architect your data using Elasticsearch. So in summary, these are the databases we've talked about today. Tiny weeny slides online. Let's talk about the questions that you should be asking. You want to ask about how big your data is. If it gets big enough that you need to partition it, you will have to distribute it across multiple systems. If you don't, you're just going to face bad performance issues over time. It's going to get worse and worse. And you need to start thinking about which database am I happy to put it in. You need to start thinking about, do I want to trade off availability or do I want to trade off consistency? And it's important that you make, it's not the end of the world if you make the wrong call, but if that is a big problem further down the line, then you will need to think about the costs of re-architecting it. If you have the luxury of not having to distribute your data, then sometimes you can get these databases, which either use high fidelity data models or potentially very specific data models that are low fidelity, as in there's very little substance behind it. And if you do that, then sometimes you'll get more stuff out the box for free. So that's the sort of things we're talking about, time series databases. You get that for free. If you're not happy to pay lots of money, you may have to sacrifice it. You may have to make sacrifices when you're doing your database. If you have a low budget, you won't be able to use Oracle on your brand new startup company. I'm really sorry about that. And you have to think about what is actually going to be consuming your data. Think about the queries that you will be running. Think about what the customer might want. Think about future requirements, just to prevent costly re-architectures down the line. Your system is unique. Everybody here who's writing a system, writing code, has got a different requirement. Nobody is writing something that has been written before, because if you are, why are you writing it? Just use what was written before. So your system is different. So actually think about the ways in which it is different. Think about the fact that SQL, which might be your go-to database, might not be the right thing, because there are a wide range of databases out there, and do consider each of them on their own merits. Thank you. Any questions? Hello.
Can you just build a tool with all that information so I can plug in my requirements?
There are excellent blog posts out there. Obviously, databases and open source libraries are springing up daily. Almost all of them are awful. So maintaining such a list is very hard to maintain. There is a very good one that I don't know the URL of off by hand, but just to start typing in a number of different NoSQL databases, and you will find that blog post that has a lot of very good pros and cons. I will try and turn, the slides will be going online, I'll try and turn it into something useful at some point as well. Hello.
I have very little experience of NoSQL.
Yes.
Like the idea of doing statistical summaries seems quite difficult in the way that I can picture it to MySQL. Is that true?
So the first thing so the question was statistical summaries in NoSQL, good or bad, hard or easy. The first thing to remember is that NoSQL isn't one thing. SQL is one thing, and NoSQL is anything that's not that. So if you take your document store database, which has all of your data dotted everywhere, then yes, doing aggregate statistics, doing any kind of data analysis on that will be very, very difficult. Trying to find everything that matches a query in any key value store, trying to filter data based on a property of that data is going to be very, very difficult, because they don't build indexes in. There are some NoSQL databases, specifically column store databases, which rather than storing rows close to each other on the file system, so if you have a row with 5 columns in SQL, those 5 columns for that row will be stored next to each other in a file. But in column store file systems, everything in the column will be stored first rather than the rows. And in that case, if all you want to do is aggregate over every item in that column, doing very simple full data analysis, then that's going to be much faster than in MySQL. So it goes back to thinking about the kinds of analysis that you want to do. I think it's definitely true that MySQL gives you, at this point in time, the broadest range of techniques available to you. But if you have obscure requirements, if you have very large amounts of data, and if you have very tight time conditions, it might be possible to find solutions that are better. But I think what is true about NoSQL solutions is that they're much more niche solutions. That you probably, if you were setting up a wide range of data analytics package tomorrow, MySQL would probably be the right tool to use, just because you're not closing any doors to yourself the way that you would with some NoSQL solutions. If that makes sense?
Yeah.
Excellent. Cool.
Would you consider using a number of different database types in the same application? So for the geolocation stuff, you might farm that data off into one place and then other data off into another database type?
Yeah, absolutely. You can definitely consider using multiple databases. You have to, whenever you start using another database, you do have to be careful of the cost of maintaining 2 different kinds of data. If you're going to be using the same data in 2 different databases, you have to start thinking about, is it possible for them to diverge? If it does, can I resolve that? Is there a cost involved there? And so the more databases you add to a system, the more expensive it gets. But people do use multiple databases if they have multiple use cases. Elasticsearch is very keen to start getting libraries out that allows it to integrate with every other database. I know that Elasticsearch and MySQL, that library already exists. Elasticsearch Neo4j is currently being developed by the Neo4j community. So it is definitely possible. Just be aware that for every database you add more complexity, you add more chance for your data going out of sync, you add potentially more cost down the line. One big famous pattern involves using Logstash, which is a big logging database. You just throw all of your log things in there, and then using Neo4j. So whenever you make a transaction in your database, whenever you change something in your database, you throw that into Logstash. You then have a batch job, which is processing the end result of running all of these transactions onto your database, and then using that to inform the shape of this high-fidelity database. So essentially, you're getting very, very cheap writes because you're writing it into a logging database, which is just very famous for throwing stuff in there. And then you're still getting the data model, and you're getting that maybe about half an hour behind. And that's a model that's kind of working for some people. You get immutability in your data, and then you're still getting a high data model, even if it is slightly out of sync. So that's another case in which that can be used. Cool.
You mentioned performance and SQL compared to Neo4j, but you didn't actually said something about what SQL's performance is. You didn't actually say anything about compute, how more performant Neo4j is.
Yes, there is a table out there. Again, I'm sorry I didn't put it in my slides. This is a story that always gets told at the Neo4j conference because it's they like patting themselves on the back a little bit about this. And a big social media company came up to them. They never say who it is. I'm going to guess it's LinkedIn. LinkedIn came up to them and said, "Okay, give me a kind of prototype. Give me a kind of guess as to how quick your performance will be." And they were doing a friends of friends network. So I want to find in a SQL database who my friends are, and then who their friends are. Friends of friends, that's a depth of 2, depth of 3, depth of 4, and depth of 5. For the depth of 2, I think they were talking, 0.7 seconds for SQL, 0.07 seconds, or something like that for Neo4j. But by the time it gets up to the depth of 5, Neo4j is doing it in 3 seconds, and MySQL runs out of memory and crashes your computer. So that table is out there. Do have a look. If you are worried about performance, if that's a really key requirement in your database, spin up an instance. A lot of these databases will do free trials. Have a quick play, build a prototype. This is a system that's going to shape your application for years to come. Don't make this decision very quickly in a pub. Make it after a week's kind of quick V1 prototype. Okay.
I think we'll have to finish it there.
Okay. Thanks very much.